All right, so in this video, we're going to start to look at kind of the stoichiometry of reactions involving gases. So if we look at the example here, actually, I'll go back one slide, excuse me. If we look at the example here, and we'll still kind of thinking about the ideal gas law, thinking about this reaction at the bottom. So nitrogen plus 3 hydrogens gives us two ammonia. So this is the Haber process. With the gases, we can think about these stoichiometric coefficients as molecules. We can still think of them as moles. But if we've got these under the same conditions, we can also think about them as volumes. So 1 volume of nitrogen requires 3 volumes of hydrogen, and that'll give us 2 volumes of ammonia, excuse me, I keep saying ammonia. So when we look at the example here, propane, so if you ever used a grill, likely that it used propane, so you can get them from like the gas stations and supermarkets and things like that. But that's going to be the gas that's used for cooking in those types of grills. And we want to figure out what volume of oxygen at 25 degrees Celsius and 760 torr, so it's 1 atmosphere of pressure, is required to react with 2.7 liters of propane under those same conditions. And for this one, we're going to assume that the propane undergoes complete combustion. So we're assuming all 2.7 liters of that propane is going to get fully reacted with. With this question, we're going to see with some of the later ones, we'll go a little bit further. This one, we're just kind of focused on volumes to start. But we know the volume of propane, and then we have the condition. So what we could do is figure out a whole bunch of stuff and kind of make it more complicated than we need to. But if we just have the balanced chemical reaction, we know the volume of propane. We know it's under the same conditions as the oxygen. So those volumes are just going to be equivalent as long as we account for the stoichiometric coefficients there. So like I said, the first thing we need is just that chemical equation. So if we look here, thinking about this as a combustion reaction, so we're going to be taking that propane and reacting with oxygen, the only two things we have. And that's going to give us carbon dioxide and water. So we want to make sure we have it balanced. We don't want to just say, okay, C3H8, O2, just 1 and 1. We got to think about how they're going to combine so we have this balanced chemical reaction so that we're conserving mass. So C3H8 plus oxygen gives us carbon dioxide and water. But since we have 3 carbons in propane, we need 3 carbon dioxides to account for those carbons. Now we got 8 hydrogens, so we need 4 water molecules to account for those. And now on this side, we've got 3 times 2 for the oxygen. So we've got 6 oxygens here, 4 more from the water. So we've got 10 total oxygens. So we need a 5 in front of the oxygen on the left to give us 10 as well. So now with this reaction, we're saying 1 mole of propane plus 5 moles of oxygen gives us 3 moles of carbon dioxide and 4 moles of water. But again, we can think about this in terms of volumes as well, because we're saying these are under the same conditions. So this now means we've got 1 volume of propane for every 5 volumes of oxygen. And since we knew the volume of that propane already, 2.7 liters, we can just multiply that by the stoichiometric coefficients. So again, kind of the same thing as when we were thinking about the stoichiometry in the earlier chapters, whether it was solids or solutions, we can use those units. So for every 1 liter of propane, we need 5 liters of oxygen. So since we have 2.7 liters of propane to start, that means we're going to need 13.5 liters of oxygen to fully react with that amount of propane. And if we look at the one at the bottom now, if you want to practice with this one on your own, just pause the video. But if we look at this one now, an acetylene tank, so it's used for welding, provides 9,340 liters of acetylene gas, which has a formula C2H2 and it provides that volume at 0 degrees Celsius to 1 atmosphere. It always has that formula. How many tanks of oxygen, each providing 7,000 liters of oxygen at STP, will be required to burn the acetylene. So we've got, in this case, the chemical reaction already given. So 2 moles of acetylene for 5 moles of oxygen gives us 4 moles of carbon dioxide and 2 moles of water. But again, we can think about those in terms of volume. And the important piece here again is the conditions for oxygen and the conditions for that acetylene are the same. If it wasn't, we wouldn't be able to just easily relate these with the stoichiometric coefficients. But since they're under the same conditions and we're assuming each gas behaves identically with that ideal gas law, that's why we can just use these coefficients to figure out the relationship there. But now this one, we know the total amount of acetylene. So what we can do is, all right, so we know the total amount of acetylene, 9,340 liters of C2H2. But then what this is telling us is we've got 7,000 liters of oxygen. And actually, I'm getting ahead of myself because we want to go. So we have 5 liters of oxygen for every 2 liters of C2H2. So now this is telling us how many liters of oxygen are we going to need to react with that much acetylene. But we want to figure out how many tanks of oxygen are we going to need. So now what we have is 1 tank is equal to 7,000 liters of O2. Calculator. So I don't remember, right? Can't do that. So 2.5, so it's going to be a little over 1 times 2.5. I'm going to guess it's going to be like 3 something. Yeah. So 3.34 tanks is just the solution. I just don't have my calculator, so I can plug that in. But again, just the only reason this works is because we've got the same conditions for those two gases. That's why we can just simply use the stoichiometric coefficients to relate those volumes. Kind of just the same way we relate the moles. So with this one, again, just another practice one. So if you want to practice that one, just pause the video. I'm just going to skip through this one though. This is going to be that same idea. Just looking at the equation, we've got to write the chemical reaction in this case. So just note in this case, it's C2H4. So we've got 2 extra hydrogens there. So we'll wind up with an extra water molecule. So we should wind up with an extra oxygen molecule on the left. Actually, you'll have to do a little bit more balancing because you'd wind up with half an oxygen molecule on the left. So you'd have to double everything. But with this one now, when we're thinking about these reactions, we're not just going to be focused on volume. So when we're looking at the stoichiometric coefficient, we've already kind of seen it. The first thing we still always want to make sure we do is balance that chemical equation. If we don't have those stoichiometric coefficients, we're still not going to be able to relate these substances, even if we're not doing it just with volumes like we did before. We're not going to have that correct relationship. So we always need to have that stoichiometry. And then just like with the past ones, we want to make sure that if we're given a value of a gas sample in mass, that we first convert it to moles so that we can actually use those stoichiometric coefficients to relate those substances from one another. And then it'll be what the third step here is talking about. And then with the fourth one in this case, make sure as we're solving these different practice problems, and then the same thing with questions on quizzes, exams, homework, whatever, that you're focused on what we're looking for. Because with the final answer, in some cases, we might be looking for the pressure that gas exerts. We may be figuring out moles, we may be figuring out mass. So there's a bunch of different things we could be solving for with these ones. So we got to make sure that when we're setting up our calculations, we're setting it up to get that piece that we're interested in. So with this one, an automobile airbag or automobile airbags are caused to inflate during crash or sudden stop by the rapid generation of nitrogen gas from sodium azide according to the following reaction. So sodium azide is sodium with 3 nitrogens, and that's going to decompose into sodium and nitrogen gas. There must be something else to react with this sodium because that'd be crazy if we just left pure sodium. So I would assume there's something else going on with this reaction, not just leave pure sodium, because that's going to be extremely reactive, extremely dangerous. But If an airbag has a volume of 36 liters and it is to be filled with nitrogen gas to a pressure of 1.15 atmospheres at a temperature of 26 degrees Celsius, how many grams of sodium azide must be decomposed? All right. So with this one, let me actually get rid of this. All right. So for this one, again, we want to figure out how many grams of sodium azide ultimately decomposed. But first, we have to figure out how much of the nitrogen was actually produced in terms of moles. So we're going to take the gas law and rearrange it, and we'll have PV divided by RT. So with this one, we've got a pressure of 1.15 atmospheres times parentheses 1.15 atmospheres times 36 liters. And then we're going to divide that by R times 299.2 Kelvin. And when we do that, we're going to get 1.69 moles of the nitrogen gas being produced. So now that we have that, what we can do is just essentially use the stoichiometry that we've done in the past. We're going to be relating one substance to another. We got the moles of nitrogen, so now we can just go directly to moles of the reactant, and then we can use the molar mass to go from moles of that to grams ultimately. So we'll have 1 mole N2, and then I'm actually going to insert an equation so it's a little bit easier to see the dimensional analysis. And based on the chemical reaction, we get 2 moles of NaN3 for every 3 moles of N2. Equation, insert another fraction. And now for every 1 mole of sodium azide, NaN3, we're going to have a molar mass of 65.01. So that comes from adding up 1 nitrogen, or 1 sodium, excuse me, with 3 nitrogen. So about 23 for the sodium, 14 for each of the nitrogens. And that'll give us now a mass of 73.2 grams of that sodium azide. So with it, the second piece here, the stoichiometry, is something we've already seen. It's just in order to get the number of moles, we're now just utilizing that ideal gas law. We've got to kind of think about what do we have, what can we use to get to moles, and then once we get moles of something, now we can utilize that chemical reaction, that chemical equation. So similarly here, if you want to practice with this one, now we've got oxygen generators in some airplanes are based on a chemical reaction between sodium chlorate and iron. So you can see that chemical equation below. And remember, with these equations, we always want to make sure that they're balanced. So in this case, we've got 1 sodium on each side, 1 chlorine on each side, 1 iron on each side, and then we've got 3 oxygens on the left, 2 oxygens here, a third one on the right. So we've got a balanced chemical equation already. So we don't need to add any coefficients to this one. But we want to figure out how many grams of that sodium chlorate are needed to produce 125 liters of oxygen at 1 atmosphere and 20 degrees Celsius. So again, we're going to have to use the ideal gas law to figure out how many moles of oxygen we have. Then we can use the chemical equation to go from moles of oxygen to moles of sodium chlorate. And then we can use the molar mass of that substance to then convert it to the grams that we're looking for. Again, let me exit out of this so I can actually type. Hopefully the typing is a little bit easier than when I write. Sometimes with the mouse, it's just difficult. And then when I try to do it on the iPad, or my tablet rather, it's just sometimes a little messy as well. But again, we're rearranging the ideal gas law to solve for moles in this case, so we can figure out how much of that oxygen we have. So we're going to have pressure times volume over the gas constant and temperature. So here we're going to have 125 liters times 1.00 atmosphere divided by R, capital R. And then we've got a temperature of 20 degrees Celsius, but again, we always want to make sure these are in Kelvin. So we'll have 293.2 Kelvin. And when we do that, we're going to get a value of, where do I have that? 0.20 moles of oxygen. So that's how much oxygen's going to be occupying that 125 liters at that temperature and pressure. But we want to figure out how much of the sodium chloride is needed to produce that amount. So again, we're going to use our chemical equation, use those stoichiometric coefficients. And if we think about it, we've got 1-to-1 for all of those different substances. So if we had 5.20 moles of oxygen being produced, we would need 5.20 moles of the sodium chlorate to start. And then once we have that, we can use the molar mass of that substance. Oops. So if we add up 1 sodium, 1 chlorine, 3 oxygens, we're going to get a molar mass of 106.44 grams per mole. So the mole is going to cancel, we'll just be left with grams. And what we're going to see in this case is we should wind up with 553 grams of that sodium chlorate. But again, the second piece is something we've already been doing since the previous quarter. It's just now in order to figure out how much of the substance we're working with in terms of the gas, we need to use the ideal gas law to get that mole. But once we get that, it's again just using the chemical equation to relate these two substances to get the value that we're interested in. All right, so this one kind of a similar idea. We're still going to be using the ideal gas law. We're still going to be using the chemical equation. It's just now we're going to be kind of doing it in the opposite order. So the previous one, we used the ideal gas law to figure out how many moles of a substance we had. Then we can use the chemical equation. Now in this case, we're going to use the chemical equation to figure out how many moles of a substance we have. Then we can use the chemical, or we can use the ideal gas law to figure out the volume of this substance. So if we look at the question, what volume of hydrogen at 27 degrees Celsius and 723 torr may be prepared by the reaction of 8.88 grams of gallium with an excess of hydrochloric acid? So in this case, we know how much of the reactant we have. We're trying to figure out what volume of hydrogen would be produced. So what we've got to do is go from grams of gallium to moles of gallium. Then we can use this chemical equation to go from moles of gallium to moles of hydrogen. And then using these conditions, using the ideal gas law, we can figure out what that volume is going to be. But again, just remember, with that ideal gas law, we'll have to convert both of these units. So we'll have to change that to 300 Kelvin. And we'll have to change this to some amount of atmosphere. So it's going to be less than 1 since there's 760 torr in an atmosphere. But looking at this one, again, we're just kind of doing it in the opposite order of the previous ones. So we can look at the amount of gallium to start, use that molar mass just to get the moles of gallium. And then we can use the mole-to-mole ratio here to figure out how many moles of hydrogen would then be prepared from that starting amount of gallium. So if we started with 8.88 grams of gallium, we're going to wind up producing 0.191 moles of hydrogen. And now that we know the amount of gas we have, we can use the conditions, we can use the ideal gas law to figure out that volume. So you can see here, we're just rearranging the ideal gas law to solve for volume. So we have the moles of hydrogen times the gas constant times that temperature. So again, changing Celsius to Kelvin. And then the same thing with torr to atmosphere. So 723 divided by 760 in order to get it to atmospheres. But now that we plug all that in, we'll see that gas sample is going to occupy a volume of 4.94 liters. So if we want to practice with another one here, sulfur dioxide is an intermediate in the preparation of sulfuric acid. What volume of sulfur dioxide at 343 degrees Celsius and 1.21 atmospheres is produced by burning 1 kilogram of sulfur in excess of oxygen? So with this one, again, we know how much of a reactant we have. We can use the chemical equation to figure out how much of a product we're going to produce. And then based on that number of moles, based on the conditions we have, we can solve for that volume. But with this one, we need to actually get the chemical reaction. So we're going to have sulfur plus oxygen going to sulfur dioxide. So with it, it looks like it's balanced as it is. And with this one, it requires a little bit extra information. We don't really focus on sulfur a ton, but we talk about diatomic molecules, so things like hydrogen, nitrogen, oxygen, fluorine, all of the halogens are diatomic in their pure elemental form. What we see with sulfur is similar, But instead of being diatomic, instead of having 2 of those sulfur, it's actually going to have 8 of them. So when we look at the balanced reaction here, that means we'll need 8 sulfur dioxides on the right, which means we'll need 8 oxygen molecules on the left. So that's going to be our balanced chemical reaction. And now that we have that, we can do 1,000 grams of, actually, let's do this in the equation. So we've got 1,000 grams of S8. And then with this, we can use the molar mass of sulfur. So since we've got 8 of those sulfur atoms, we'll do the mass of sulfur times 8 will give us 256.56 grams. And that'll be 1 mole of S8. So then using the balanced chemical reaction, we see that for every, what we're looking for, 8 moles of SO2, we need 1 mole of S8. So this means when we go through and calculate this, this means we're going to produce 31.2 moles of sulfur dioxide from that amount of sulfur to start. And now with the second piece of this one, we want to figure out the volume that sulfur dioxide is going to occupy. So we'll do nRT divided by pressure. So we'll have 31.2 moles times R times the temperature. So again, Celsius needs to be converted to Kelvin. So instead of 343 Celsius, we'll plug in 616 Kelvin because we're going to add 273 to that. Then we're going to divide it by the pressure, 1.21 atmospheres. And that's going to give us a volume of 1.30 times 10 to the third liters. So with this one, I think you'll get 1,301 liters. But we only have 3 sig figs. That's why in this case, we actually do need to use scientific notation. There's no other way to write this value with just 3 sig figs. Because if we did the whole number just as a regular number with a decimal, that would be 4 sig figs. Without a decimal, it would only be 2. So if we only want to indicate that one of these zeros is significant, because again, this would really be that number. But if we have it written like this, that's only 2 sig figs. If we put a decimal there, now both of those zeros are significant, so it becomes 4. So if we only want this portion of it to be significant, whoops, we can only do that with scientific notation. Same answer. All right. And then with this, I think this might be this final piece of this video. But with this one, what we're looking at is a reaction, then we collect a gas over water. So we've actually had a lab that's actually exactly identical to what we're looking at here. The setup actually with this portion of it was a little different, but we had potassium chlorate in a test tube. We mixed it with manganese dioxide as a catalyst, but we heated it up so it decomposed to give us oxygen gas. And then we would collect that, have it travel through the tubing, collect that in our flask, and then would displace some amount of water. And now that I'm thinking about it, this may actually be an easier setup, so we might try to do that in the future. But with this, and as we saw in the lab, the reason this works is because ultimately the pressure in our flask, or in this case, the upside down beaker, is ultimately going to be equal to the atmospheric pressure. So as we have the gas come through here, it's just going to displace some amount of water until the pressure on the outside is equal. So as the pressure in the container is greater, it's going to force more of the water out. If the pressure in the atmosphere is greater, it would force more of the water back in. So that's going to happen until it just evens out the pressures there. So then when we look at this container, thinking about Dalton's law of partial pressure, we're now going to have the pressure from whatever gas we produced. So in our case, it was the oxygen gas from the decomposition of potassium chlorate. You could do it with other reactions and have some other gas being collected here. But in addition to the gas that's being produced from the reaction, we're also going to have some amount of water vapor just from the vapor pressure of water. So we need to account for both of those pieces. And again, this is going to be why we use Dalton's law of partial pressure, because we're going to know that the total pressure within this container is going to be equal to the atmospheric pressure. So then if we know the temperature of this water, we can get the vapor pressure, and then that's going to be one of our two components. So if we know the total pressure, we know the vapor pressure, we can subtract those to get the pressure of our gas of interest. So you can just see here, this is just a table with the vapor pressure of water at a whole bunch of different temperatures. So you can see as the temperature increases, the vapor pressure increases. And that makes sense because as we heat up that water, we're going to get more and more of it moving into the gas phase. So now that vapor above our liquid is going to be exerting more pressure. And that's all vapor pressure is, just the pressure from the vapor above a pure liquid. So in this case, if you think about it, you'll put water in a little container and then just measure the pressure of that water vapor at these different temperatures. And if you look here at 100 degrees Celsius, we have a vapor pressure of 760 torr, equal to 1 atmosphere. So that's just the boiling point, or the normal boiling point, is where the vapor pressure of that substance equals atmospheric pressure. At that point, we're just going to have the substance start to boil. And that's why you can see above 100 degrees now we have vapor pressures greater than atmospheric pressure, because we're going to get all of that substance basically moving into the vapor phase. But now if a question like this, again, similar to what we did in the lab, if 0.200 liters of argon is collected over water at a temperature of 26 degrees Celsius and a pressure of 750 torr in a system like the one we just saw, what is the partial pressure of argon? So with this, you look at it, we've got a volume, we've got a temperature, we've got a pressure, but we don't have the moles for argon, so we can't use, I guess we could use the ideal gas law and solve for moles of argon, but that's not really useful with this question. Because also with it, we don't know, at least right away, what pressure of that 750 is coming just from the argon. So what we could do is kind of go back to a table like this. If you think about it, 26 degrees Celsius. So if we go back here, 26 degrees Celsius is going to have a vapor pressure of 25.21. So if we're thinking about a image like this now, the atmospheric pressure in this case is 750 torr. So a little bit less than 1 atmosphere, but pretty close. But 750 torr. So after this reaction kind of equilibrates, the pressure inside our container is going to be 750 torr as well. So if we know the water has a temperature of 26 degrees Celsius, that means the vapor pressure of that water is going to be 25.21 torr. So if our total is 750, but 25.21 of that is coming from the water, that means the other 725 is going to be coming from the argon. Again, we can do that just based on Dalton's law of partial pressure. So the total pressure of that system is going to be the sum of all of the pressures of the different gases. And in this case, it's just going to be the vapor pressure of water plus the pressure from the argon that's being produced. And again, it's 750 for the total minus the 25.2 from the vapor pressure of water, just giving us 725 overall there. And if we look at another one, a sample of gas, a sample of oxygen collected over water at a temperature of 29 degrees Celsius and a pressure of 764 torr, has a volume of 0.56 liters. What volume would the dry oxygen from this sample have under the same conditions? So with this one, if we go back again, 29 degrees C, so we'll see 30 torr. So 764 torr overall. That means 30 of it's coming from the water. So that means 734 of it is going to be from the P 764 minus 30 gives us 734 torr for the oxygen. And now what we want to do is figure out the volume. So now we're going to use the ideal gas equation again. Volume is equal to nRT. All right. So with this one, I just looked to make sure that it was saying the same conditions of temperature and pressure. And that is the case. And with it, we don't actually even need to use this equation because we don't have moles. But what we can do is kind of similar to kind of the mole fraction. If we think about 734 torr divided by 764 torr, what that'll give us is kind of the mole fraction of what gas is this? Oxygen in the total mixture. 734 divided by 764. So we get 0.961. And then what we can do is use that and just multiply it by the same volume, 0.961 times, what was the total volume? 0.560 liters. And then with this, and again, this only works because with the ideal gas law, every sample, regardless of what it is, it behaves similarly. So now if we have a full 100% of this mixture, it's going to take 0.560 liters. But if we're thinking about just 96.1% of it, or 0.961 mole fraction, we can figure out just the volume that the individual component would occupy, 0.538 liters there. 537. All right. And then with this, just a kind of related piece is when we think about these gases, you're thinking about global warming. One thing that people like to point back in history about is kind of the cyclical nature of warming and cooling within the planet. So this graph is carbon dioxide concentration versus time. But if we had temperature versus time, we'd see a similar kind of thing in terms of temperature increasing and decreasing, just because it's a cyclical pattern of the Earth to kind of go through different periods of heating and cooling. That's why we've had different ice ages and things like that. But with it, the way that we can determine the information about the climate in the past, both in terms of temperature and the composition of the atmosphere, is by looking at snow samples. So if you think about like at the North Pole, there's essentially just a record of what the Earth was like in the past within the snow itself. So there's huge layers of snow, and within that snow, there's just air pockets. So what they can do is what's known as coring. So they essentially just take this big cylindrical kind of machine and then push it down into the snow, and it takes out an ice core. So just a big cylinder of ice. And then the further you go down, just essentially the further back in history that we're looking. So they can look at the composition of the gas in those air bubbles. And then based on the ratio of like oxygen to one another, or the different isotopes of oxygen, I should say, they can determine what the temperature was like, and they can look to see what the carbon dioxide concentration was like as well. And one thing that climate change deniers like to point out is that there is a pattern of heating and cooling within the Earth's history. But what they conveniently like to ignore is that within the last 150, 200 years or so, we've seen a extremely sharp spike in the concentration of carbon dioxide within the atmosphere. So it corresponds with the Industrial Revolution, when humans started to burn fossil fuels in large quantities. So what we can do is looking at the carbon dioxide concentrations of the past, see that recently it's spiked much higher than it's ever been, and this actually isn't even the current value. So currently it's at about 420 parts per million. So much higher than it's ever been in the past. You can see at the most it kind of spiked at about 300, other than the past couple of centuries. So when we're thinking about the planet, carbon dioxide is the greenhouse gas we focus on the most because it's the one we produce in the largest quantities. And that's when we're thinking about legislation, we're thinking about designing buildings, and just planning for the future in general. One of the things that we need to be most concerned about is the carbon dioxide into the atmosphere, because not only is it affecting the atmosphere, affecting global warming, but this carbon dioxide into the gas phase also then dissolves into the oceans, which then makes the oceans more acidic, and that has impacts on coral reefs and things like that, those different sort of shelled organisms. And we'll talk about that when we look at equilibrium as well. But I just wanted to bring this up because the textbook has this image, and it's an important piece with a lot of the climate change deniers. They like to point to the cyclical cooling and heating of the Earth in the past, but they like to ignore that the carbon dioxide temperature, the carbon dioxide concentration has spiked, in addition to the temperature also being higher than it has been in the past. But then with the last video, it'll start to just look at kinetic molecular theory. So we're going to get a better understanding of what these gas molecules are doing in terms of temperature. How does that affect the energy? And then we'll also look at kind of the real gases as well.